Hypersonic spaceplanes represent one of the most ambitious directions in aerospace engineering, a vehicle capable of operating both as an aircraft and a spacecraft. Unlike traditional launch systems that rely on vertically launched expendable rockets, spaceplanes are designed for runway operations, full reusability, and rapid turnaround between missions. The defining feature of a hypersonic spaceplane is its ability to sustain flight at hypersonic velocities, typically defined as speeds above Mach 5. At these speeds, aerodynamic behavior changes dramatically. Shock waves intensify, air molecules begin to dissociate due to extreme temperatures, and conventional propulsion systems become inefficient. As a result, hypersonic spaceplanes require specialized propulsion systems capable of operating efficiently across a wide speed envelope. One of the most discussed propulsion architecture is the combined cycle engine. These engines transition through multiple operating modes as velocity increases. At low speeds, the vehicle may rely on turbofan or turbojet propulsion. As velocity increases into the supersonic regime, ramjet operation becomes viable because incoming air compression can occur without rotating compressors. Beyond approximately Mach 5, scramjet propulsion becomes necessary. A scramjet or supersonic combustion ramjet allows combustion to occur while the airflow inside the engine remains supersonic. This eliminates the need to slow incoming air to subsonic speeds, which could otherwise create excessive drag and thermal loads at hypersonic velocities. Scramjet engines therefore allow sustained atmospheric hypersonic flight while using atmospheric oxygen instead of carrying onboard oxidizer. The fundamental aerodynamic challenge of hypersonic flight is thermal management. Aerodynamic heating increases rapidly with velocity and is approximately proportional to the cube of flight speed. This relationship can be represented as Q is proportional to V cubed, where Q equals aerodynamic heating rate, V equals vehicle velocity. At Mach 8-10, surface temperatures can exceed 1500-2000 degrees Celsius depending on altitude and atmospheric density. Conventional aerospace materials such as aluminum alloys cannot survive these temperatures. Hypersonic vehicles therefore require high temperature materials such as titanium alloys, nickel-based superalloys, ceramic matrix composites, or reinforced carbon-carbon structures. Another key engineering challenge is maintaining structural integrity under extreme thermal gradients. As the vehicle accelerates, different sections of the structure heat unevenly, causing thermal expansion that can generate significant stresses. Designers must therefore incorporate thermal protection systems similar to those used on spacecraft during atmospheric re-entry. From an aerodynamic perspective, hypersonic spaceplanes typically employ highly optimized lifting body or waverider configurations. These shapes are designed to capture and ride the shock wave generated during hypersonic flight, effectively using the shock wave itself to increase lift and reduce drag. Waverider geometries allow vehicles to maintain favorable lift-to-drag ratios even at Mach numbers exceeding 8 or 10. The operational concept of a hypersonic spaceplane usually involves horizontal takeoff from a conventional runway. The vehicle accelerates through multiple propulsion modes until it reaches hypersonic speed and extremely high altitudes, often above 80-100 km. At this point, it can deploy satellites, perform reconnaissance missions, or act as a rapid response launch platform. Compared to conventional rockets, the primary advantage of spaceplanes lies in reusability and operational flexibility. Traditional rockets are largely expendable systems, with major components discarded after launch. Spaceplanes, in contrast, are designed for repeated flights, potentially enabling aircraft-like operational cycles with much lower cost per mission. Several experimental and conceptual systems illustrate this concept. The X-43 and X-51 programs demonstrated scramjet propulsion at hypersonic speeds. More recently, aerospace research programs have begun exploring reusable hypersonic vehicles capable of combining air-breathing propulsion with rocket propulsion to achieve orbital velocities. Such vehicles could operate using a hybrid propulsion architecture. Air-breathing engines would accelerate the vehicle to extremely high Mach numbers within the atmosphere, drastically reducing the amount of onboard oxidizer required. A rocket mode could then provide the final acceleration required for orbital insertion. This approach could dramatically reduce launch mass fractions and improve mission economics. In strategic terms, hypersonic spaceplanes represent a transformative capability. They could enable rapid global reconnaissance, ultra-fast satellite deployment, and responsive space operations within hours rather than weeks or months. However, the engineering barriers remain significant. Thermal protection, propulsion integration, structural durability, and guidance at hypersonic speeds remain among the most difficult problems in modern aerospace engineering. Despite these challenges, ongoing research suggests that hypersonic spaceplanes may eventually become a central component of both civilian and military space infrastructure, fundamentally reshaping how humanity accesses and operates in near-Earth space.